The last week we discussed about we started chapter number 4 and we discussed about the fluid kinematics and we discussed flow description. We discussed about the Euler equation, the Lagrange equation, sorry, the Euler approach and the Lagrange approach, and we discussed about the material derivative. And we came to know that material derivative is d by dt of the any function. It can be any function. The material derivative is also called total derivative, is equivalent to partial by partial t of that function plus u into partial by partial x of the function plus small v into partial by partial y of the function, and finally w into partial by partial z of the function. It is like that. This is called the material derivative or the total derivative of any function, where u, v, and w are the velocity components along the x, y, and z direction of the velocity field or the velocity vector. The velocity vector v is equivalent to ui plus vj plus wk. So u, v, and w are the components of the velocity along x, y, and z direction. And then we solved some problems related to the is there any question from the last lecture or any question regarding the problems I gave you as home assignment? Is everything clear?
सर वो लास्ट लेक्चर में लास्ट प्रॉब्लम हमने बीच में छोड़ा था, आपने कहा था वहीं से वो करेंगे.
Which problem? Which problem?
सर जिसमें वो डिफरेंशियल इक्वेशन तक पहुंचे थे और उसको सॉल्व करना था. ये आई थिंक ये जो सेकंड लास्ट है इस स्लाइड पे.
Okay, just to giving you an idea about that problem. इसको जल्दी quickly से डिस्कस करते हैं. Let me write the statement there. So in this problem, we were given two functions of the velocity, that is u, the u component of the velocity, and the v component of the velocity, provided that c is a constant. And it is asked that show that these are the components for this equation for the streamline x square y minus y cube by 3 equal to constant. So what we know is that dy by dx is equivalent to v by u, right? So if we take v and u, we come to know that minus 2 xy, c will cancel with c, and divided by x square minus y square. This is where we left, right?
सर ये कंप्लीट हो गई थी.
And now we want to show that this is the equation for this function u and v. So in order to do that, we see that we cannot separate the variables in this form because it is an implicit form, right? Right? We cannot separate the variables in this equation, so we cannot get this equation from this form. So what we can do is we can take the derivative of this equation, that is x square y minus y cube by 3 equal to constant. If we can take the derivative of this equation and prove that it is equal to this, the derivative from this equation is equal to this, then these two components are for this equation, right? So what we do is we just apply the differential to the both side of the equation, that is d x square y minus y cube by 3, and on the right side when we take differential of a constant it becomes 0. The first function x square y is u into v form, multiplication of two functions, so we take the derivative one by one. First we take x square as constant, then we'll have differential of y will be dy, right? Then we take the differential in the other form keeping y constant, then the differential will be y 2x dx, and finally we'll have 3y cube 3y square by 3 dy equal to 0, right? 3 will cancel with 3. We can take common dy part, these two we can take dy part as common, so we get x square minus y square into dy equal to minus 2x y dx, and rearranging we get dy by dx equal to the same what we got from the velocity functions, right? Is it the same? Is it equivalent to the one we got from the velocity function?
Yes, sir.
Yes.
So hence we have proved that this equation of streamline is for those velocity functions. Clear?
Yes, sir.
Yes.
So there are few more problems on the slides. I have shared them with you. You can solve those problems. If you have any question, you can discuss them in the next lecture as well. So these are another problem and you can solve these. And they are not much difficult if you are versed with the concepts of the material derivative. So if you know the material derivative in detail, you can just solve these problems. Moving on to today's topics. Once again, we will discuss about the streamline coordinates and we'll discuss the effect of the streamline coordinates on the acceleration. That is how acceleration is varied, because we know that we calculate acceleration from the total derivative. So we'll discussing about the if we use the streamline coordinates, because till this point we have been using this normal coordinates, x, y, z coordinates. But what if we use the streamline coordinates? And from the previous chapter, we know that streamline coordinates are much more convenient to work in the fluid flow as compared to the regular coordinates x, y, and the Cartesian coordinates, right? So we'll be discussing about the streamline coordinates and how the material derivative will change if we use streamline coordinates. Okay, so you are familiar with the streamline coordinates. The streamline coordinates are basically two coordinates that are along the streamline. The coordinate along the streamline is called the s coordinate, and the other coordinate is called the normal to the streamline, as shown in this figure. So the flow plane is covered with orthogonal coordinates. Like we have to define each coordinate with each streamline. We have to define coordinate along each streamline. So for each streamline there is a relative coordinate, and then we have the normal coordinate along that. At any point the s and direction and direction are perpendicular, but the lines of constant s or constant are not necessarily straight, because the streamlines are curved mostly. So it is not necessarily that the s and n are constant or they are straight. So what we do, we define the streamline coordinates along the velocity always, because we know that velocity is tangent to the streamline. So what we do, we define the streamline direction along the velocity vector. So the velocity vector is dependent on the streamline coordinate and normal coordinate, right? Is it clear?
Yes, sir.
So we know that the velocity vector will depend on the s as well as the n direction. So the velocity vector along the streamline, this is let me explain it here. So we know that velocity vector will be having two components, right? One that is this component, that is v function of s and n, and this function is along the streamline. Clear? V is function of s and n, and this is the component along the streamline. Clear? Along the unit vector of the streamline.
Yes, sir.
Yes, sir.
Just like the component u would said that this is function of x and y and z as well as the time, but it is along the unit vector I. So here is the same concept that v is function of s and n, but it is along the streamline direction. So if we take the total derivative for the velocity field that is along the s and n direction, then we will have two component of acceleration as well. One component that is along the streamline and the component that is along the normal. So total derivative of acceleration in this case will be as plus an. And we can see that from this distribution here, from this description, we can further discuss it in detail. So in this equation, we can see that we have two components of the velocity. We know that velocity is a function of v, which is s comma n, right? And it is along the normal direction, but this streamline direction is also dependent on, because it will change with change in streamline, or it will change with change in normal. So this s is also dependent on s and coordinates, right? Is this thing clear?
Yes, sir.
So if we take the total derivative of this velocity, dv by dt, what we will be doing, we'll be taking the total derivative of these two components, right? V, which is function of s and n, and into this other function s cap, which is direction basically of the velocity, and which is again function of s and n. So which rule you will apply?
Sir, product rule.
You will apply the product rule, yes. So you will be getting the total derivative of the velocity with respect to time. This is total derivative of the velocity into s cap, right? Plus the total derivative of s cap into velocity, right?
Yes, sir.
Then you will have description for each of these, the total derivative expansion for each of these terms. This expansion is explained here. Expansion is explained here. So can you do this? There are two coordinates only. Velocity will change with respect to time, so partial v by partial t. Velocity will change with respect to the s coordinate, and s coordinate will change with respect to time. Plus velocity will change with respect to the normal coordinate, and the normal coordinate will vary with respect to time. Is it clear? And then again,
Yes,
when you apply on the s direction, the total derivative, then s direction will vary with respect to time, and s direction will vary with respect to itself, and then the s direction to time, and that. We know that this term will be equivalent to what? These two terms will cancel out, right? So we can apply the following simplifications. We know that there is no explicit dependence of velocity on time on a scale that is a streamline coordinate system. We have seen that there is no dependence of v on time, right? Because we proved that v is function of S and N. We just discussed a little bit time ago that V is function of S and N. So when V is function of S and N, there is partial V by partial T would be 0, right? There is no dependence of the streamline coordinate or the streamline direction on the time, right? So this term would also be 0. So the terms we have written for the material derivative here, that is this term would be 0, this term would be 0. Clear?
Yes, sir.
And if N is constant along the streamline, there is no change in N, which means that dN by dt would be 0 here and it would be 0 here, right? Is it clear?
सर ये n वाला सर दोबारा बता दें.
N is constant now. Particles when flowing along the streamline, N will remain constant. So when N is constant, its derivative with respect to any function, like function with respect to x, with respect to time, with respect to s, will remain 0, right?
Yes, sir.
So it means that after the simplification, we will get acceleration as this equation. That is, acceleration would be equal to v partial v by partial s into the s direction plus v square by r into n direction. We know that this is the same equation we have already studied in chapter number 3. Have we studied this equation already? That acceleration has two components, the streamline component and the normal component.
Yes,
you remember that?
Yes, sir.
So acceleration field along the streamline normal coordinate is the same as we have already studied. There is no difference in that. So using the streamline coordinates is more convenient as compared to the Cartesian coordinates. So there is only the convective acceleration. There is no local acceleration here, right?
Yes, sir.
So now the other issue is that now we have very well aware how the acceleration will vary, how we will see the material derivative and how material derivative is applied in Cartesian coordinates or and how it is applied in the streamline coordinates. But now the issue is that in most of the cases, like you are studying thermodynamics, all the laws of the physics or the thermodynamics are based on system approach. What is the system approach? Anyone? What is system?
Sir,
What is a system?
under observation, the part of the
Anything under observation, having fixed boundaries, whose mass cannot change, right? Whose mass is fixed. Mass can go in or out of the system, right or wrong? Is this statement correct if I say mass can go inside the system or outside the system? Mass can flow.
सर फिर वो ओपन या क्लोज सिस्टम बन जाते हैं.
Yes, that's the other type. So normally, if we're talking about a fixed system, there can be no mass change. The mass will remain conserved. Only there are three possible interactions with the system. That is the heat
and work, sir.
work, right? And the third one is the mass interaction when the system is flexible, right? When there is flexible system having mass changes, but we are not talking about that system. We are talking about a fixed system. So all of the laws of thermodynamics are based on a system approach, right? So when you are
Yes, sir.
so if this is your system, you're fixing its mass. So when mass is fixed, it means you are tagging the particles. You are fixing the particles. Whenever you will apply some law, you will apply that law to these particles. That law will be with respect to these particles, right? So this is basically which
Yes, sir.
approach? The Lagrange approach. You are tagging the mass. You are tagging specific mass. You are studying specific mass. So it means it is the Lagrange approach. But we have already studied that Euler approach is more convenient in fluid mechanics. Why it is more convenient? Let's say this is a body and air is passing across it. We are interested in seeing the effect of the air passing over this body, the force that this air will exert on this body, right?
Yes, sir.
So always there will be a different mass of air that will pass across this body, different with different properties, right? So we cannot use the system approach. We cannot define, okay, we are taking this mass of the air and we'll see that how this interact with this. No, we are having fresh air every time. So what we need to do, we need to define some convenient mechanism that can help us to translate these laws from system approach to the Euler approach, from the Lagrange approach to the Euler approach. That translation is provided to us by the Reynolds transport theorem. That translation is provided by the Reynolds transport theorem, or RTT. This helps us to convert system approach to control volume approach, or in other words, the Lagrange description to the Euler description. Is it clear?
Yes, sir.
And the reverse is also possible. That is, the control volume approach could be converted to the system approach if we have knowledge of the Reynolds transport theorem, and the Euler approach could be converted into the Lagrange approach. System approach is the Lagrange approach, and the control volume approach is the Euler approach. Now we need to understand the concept of the control volume. What is a control volume, so that we can develop the Reynolds transport theorem. So control volume, it can be moving, it can be deflating, it can be inflating, it can be changing volume. But right now we are discussing only the fixed control volume. We are not discussing about the deformable control volume. What's a control volume? Let's say this is a pipe and water is flowing in it. What I do, I define an imaginary surface. I define an imaginary surface across this pipe, starting from here to here, like this. Okay. What's happening? Water will come here, pass this surface, will occupy the shape of this control volume, and then move out from the surface, right? And this process will continually happen. So now I know that how much amount of water is entering my control volume, how much amount of water is leaving my control volume. So the mass of the control volume will always change, because I am not fixing this. I am only defining an imaginary boundary across which water can come inside and then go outside. If the flow rate is coming into the volume is more, then the mass of this control volume will increase. If the flow rate is less as compared to the outflow, then this volume of this control volume will decrease. The mass of this control volume will decrease. So control volume is an imaginary surface, imaginary volume. So this volume is called the control volume. This volume is called control volume. And the surfaces forming this control volume are called these surfaces are called control surfaces. All of these surfaces, they are called control surfaces or control boundaries. A control volume can be fixed, a control volume can be moving, a control volume can be deforming, a control volume can be non-deforming. There can be different types of control volume, but right now we're interested in a fixed non-deforming control volume. Right now our aim is to understand fixed non-deforming control. Is it clear, the concept of control volume?
Yes, sir.
So if it is clear, then we move to the formulation of the Reynolds transport theorem. An example of the deforming control volume could be a balloon. You define the boundary of the balloon as a control volume. So what happens when you deflate the balloon or inflate the balloon? When you inflate, the volume of the balloon will increase. So that's an example of the deforming control volume. When you deflate it, the air will discharge out. So that's a deforming control volume. So now we discuss the Reynolds transport theorem, and for that you need to understand some property. We consider some property B that is an arbitrary property. Okay, this capital B, that is an arbitrary property of the system of the control volume. We don't know what it is. And there is another property that's related to B by mass. That is small b is m times the capital B. Sorry, capital B is m times the small b. B can be any property. Let's say, for example, if I say this capital B is m, then what would be small b? What would be the value of the small b?
One हो जाएगी sir.
Yes, small b would be unit. If I say capital B is kinetic energy, then small b would be
V square by 2.
Kinetic
हाँ.
energy per unit mass.
very good. And if I say small b is capital B is momentum p, then small b would be.
Velocity. Velocity.
So is it clear the property capital B and the small b, the relationship between the capital B and the small b?
Yes.
The capital
Yes.
B is always dependent on the mass, right? It is dependent on the mass. Is it clear? So it would be an extensive property. So capital B would always be a extensive property. And small b is independent of the mass. It is the quantity per unit mass, right? It is the quantity or it is the property per unit mass. So it is the intensive property. It is small b is intensive property of the system or the control volume. And this is the extensive properties because it is always dependent on the mass. If mass will change, this property will change. Clear?
Yes.
Yes, sir.
So if B is mass times small b, and we know that mass is density into volume. So we can write B is rho into volume into small b. If I talk that B is of a small unit area property, and then we say it's the property of the whole system, what I will do, I will sum all the B's over this whole system, right? I can write that B would be
Yes, sir.
integration of the rho B with respect to the volume over the whole system, right? If it is a system property. And if it is a control volume property, then it would be the integral over the control volume rho B dV, right? Clear? depending upon the type of the system we are considering, that is system or the control volume. Is it clear?
Yes, sir.
So how we define the relationship between the two? Now we are interested in developing the relationship between these two properties. So what we do is we consider a system and a control volume. From here I will have this. Is this figure clear?
Yes, sir.
Is this figure? Okay. In this figure, let me redraw it for you in order to have better understanding, because I believe आपको इस तरह समझ नहीं आएगी. So let's say this is a pipe like this. There is inflow from here and there is outflow from here. If I try to define a system, there is red lines are my system. Okay, this is the system. What will happen with time? I'm drawing it at t equals to 0. At the same time, I am defining a control volume which is equivalent of this system. So the system and the control volume will be same at t equals to 0. So if I take any property B of the system, that should be equal to B of the control volume, right? At
Yes,
time
sir.
equals to 0. Now what happens after some time t plus delta t? We have again the same configuration. Because system is talking about a fixed mass, right? So there will be inflow from here, there will be outflow from here. But now, after time t plus delta t, what will happen? The system will move from here to here, right? But the control volume will remain
Same.
fixed at its location. Clear?
Yes, sir.
सर ये समझा रहे हैं क्यों फिक्स है कंट्रोल वाले?
क्योंकि हमने डिफाइन किया अपनी मर्जी से. We have defined it ourselves. We say it's
सर
a
हमने
fixed.
सिस्टम को भी तो डिफाइन किया था ना.
But system is about a fixed mass. System is like about a tagging a particle. I have tagged a specific volume. I have tagged a
ठीक है
specific
सर,
mass.
सही हो गया सर, समझ
So
आया.
I will keep following that mass. That's the Lagrange approach. But in control volume, we have defined it is fixed at place. Mass can enter this control volume, mass can leave this control volume, but it will remain fixed at its place. So clear?
Yes sir, clear.
So now I take that picture. So this is what happening. Okay. So the system has moved here from this location, this initial location. So if I ask you to write the properties, B system at t plus delta t should be equivalent to what?
सर the integral
Just simple property, जैसे अभी हमने लिखा ना T0 पे B system is equal to B control volume. तो T plus delta T पे क्या होगा?
So integral rho b.
There is no need for the integral this time. You will just tell me, okay, what has happened. अगर मैंने सिस्टम की मास को इक्वल करना है कंट्रोल वॉल्यूम के तो क्या हुआ होगा? The property of the control volume, right? Plus the amount which has entered the control volume, that is B1, right? Minus the amount that has left the control volume. ऐसे ही है?
Yes.
क्लियर? किसी का क्वेश्चन तो नहीं है इसमें? ये समझ आ गई है?
जी सर आ गई।
So if it is clear, just gonna. So at initial time, it is B system equals to B control volume, and at time t plus delta t, it is B control volume at t plus delta t minus B1, which is the mass entering the system, plus B2, that is the mass leaving the system. Clear? वहाँ पे शायद मैंने sign reverse कर दिए हैं. Yes, this is my plus and this is minus. The amount that is entering and amount that is leaving. B1 is the amount entering and B2 is the amount leaving. So if I want to see the time rate of change of this property, that would be partial by partial t, right, of every term. थोड़ा सा मेरे लिए वो लिखना थोड़ा सा डिफिकल्ट हो गया, सिंबल्स बहुत ज़्यादा हैं. So I'll just take this equation there. So this is the equation at t plus delta t. So we'll just take time derivative with respect to of each term. So we take time derivative here, we take time derivative of this whole term, partial by partial t. Clear? Can you do that? ये कर लेंगे ना, टाइम डेरिवेटिव तो लेना है बस, सिंपल.
उसमें सर ये जो आपने ऊपर मैस जो है ऐड की है इसमें कंट्रोल वॉल्यूम, तो ये बेसिकली आप ये सिस्टम अप्रोच को कंट्रोल वॉल्यूम अप्रोच में कन्वर्ट कर रहे हैं.
बिल्कुल ऐसे ही, राइट. बेसिकली वी आर ट्राइंग टू राइट कंट्रोल वॉल्यूम. तो मैं आपको यहाँ पे, कैन यू सी दिस पिंक लाइन? नजर आ रही लाइन जो मैं ड्रॉ कर रहा हूँ? नहीं नजर आ रही होगी, ये थोड़ी सी थिन है. अब नजर आ रही है ये लाइन जो मैंने ड्रॉ की है आपके सामने?
नहीं सर, विजिबल नहीं है.
No sir.
सर आपकी थोड़ी देर तक आती है। अब आइए।
अब
ये
आइए.
जो लाइन मैंने ड्रॉ की है इस सामने, ये जो पिंकिश लाइन है, दिस इज योर, क्या है जी आपकी?
System volume.
कंट्रोल वॉल्यूम. ठीक है. अब मैं आपके सामने ड्रॉ करूंगा रेड लाइन. ये रेड लाइन नजर आ रही है आपको? दिस इज योर सिस्टम मैंने लिखनी है सिस्टम की प्रॉपर्टी. आई हैव टू राइट सिस्टम प्रॉपर्टी बी सिस्टम इन टर्म्स ऑफ कंट्रोल वॉल्यूम. तो इनिशियली क्या था, सिस्टम और कंट्रोल वॉल्यूम इक्वल थे, राइट?
इक्वल थे सर.
But what has happened now? The system is equivalent to volume of the control volume minus this region, right? System is now equivalent to this control volume minus this region, the one region, right?
Yes, sir.
Yes sir.
And plus this region too, this new region which
Yes,
it has moved. This has happened at time t plus delta t. Initially they were same. Is it clear now?
Yes sir, clear. Okay, thank you sir.
Now we'll just take the time derivative at time equals to t. That is at initially partial by partial t. B system should be equal to at time equals to 0. It should be equal to partial by partial t of B control volume. And the other term would be time derivative of this form. So that I will take from there. Partial by partial t or so just be doing some manipulations here. The other term would be at time t plus delta t. Okay. So at time t plus delta t, we'll have B system change in property. That is B system t plus delta t minus B system at t, right? The change will be property in the property at time t plus delta t minus property at time t. Clear? And now we know that B system in terms of the control volume form. So we have just substituted the control volume functions here. So we get this. And we also know that B system at t is B control volume. We will replace this with B control volume of t. Clear? We are trying to see the difference in the change in the property with respect to time. Most of the time we are interested in this thing, right? The change in energy with respect to time, the momentum, the change in momentum, the force per unit time, we're interested velocity per unit time, we're interested in such kind of properties. So we are saying trying to have the change in system property, that is delta B system by delta t. The change in system property would be equal to B of system at final time, that is t plus delta t, minus B of system at time, initial time, right? So the delta, divide this by delta t. Clear? We know this transformation of system into control volume. We know this transformation of the system into control volume form. We have the linkage between these two properties. So in this above relation, we have just replaced that linkage. This is the B system form at t plus delta t in the control volume function, and this is the replaced by this function. Clear?
Yes, sir, clear.
Now, if we just rearrange, now we have just rearranged the equation. That is, we have combined the B control volume t plus delta t term with the B control volume at time t minus B1 t plus delta t by delta t plus B2 by t plus delta t. Is this form clear? This last form which I have highlighted?
Yes, sir, clear.
It's just a rearrangement. Now, if you apply limit delta t equals to 0 on this, what will happen? Do you remember mathematics of first year or second year, the derivative chapter number 2 of second year book?
Rate of change of the property system.
So the first term will be a derivative of the control volume with respect to time, right?
Yes, sir.
So that would be equivalent to this term. Do you understand this term? This is the ab initio method, AB method. So the first term would be representing the change in control volume with respect to time, and we can write it as partial by partiality of the integral control volume rho b dv. Is it clear this term?
सर ये रो भी कहाँ से है?
We have already studied that. Just talking about B is mass times small b, right? And mass is density times b into the volume of the small particle or the small control volume. And if we want to have it over the whole system, then we'll integrate it with respect to the control volume in case of control volume, and if it is a control volume property. And if it is a system property, then we will integrate it with respect to the system boundaries. Clear?
Okay, sir, clear.
So is this last term clear now, how we are getting the derivative form? Okay. What about B1 and B2? B1 would be density at point 1 into property in point 1 into volume 1, right? And B2 would be
Yes, sir.
rho 2 B2 into volume at point 2. So that's not difficult. And we can write volume as, now that's the thing to understand. We go back to this figure here. So let's say this is some length L2, right? And this is some length. So that is L1 and this is L2. We know that volume is, we all know volume is yes, volume is equivalent to
Derivative.
what?
सर हम वहाँ से
Density
निकालेंगे
cross
area.
mass. Density over mass.
Not that. Area into
सर AVT सर हमारे पास इक्वेशन आ गई.
into length, right?
Yes, sir.
This area would be the cross-sectional area of the control volume boundary, right? If this is the control volume, A would be this cross-sectional area, right? Into the page area, just like this. Right, this would be A, and L would be the change in this distance, right? And that we know that distance is velocity into time. Clear? So volume would be area into velocity into time. Is it clear?
Yes, sir.
Is it clear?
Yes, sir.
Yes, sir, clear.
Yes, sir.
So here we have rho into B into volume. So we have written volume as area into length for the first section. So it would be area of the first section into the velocity of the first section. That is the velocity entering, amount of the fluid entering the boundary into delta T. And similarly, B2 would be density of 2 into property at point 2 into area 2 velocity 2 into delta T. So is this relationship clear? These two relationship, are they clear?
Yes, sir.
Yes, sir.
So now there's delta T. So if we write that B1 is the inflow and we apply limit delta T approaches to 0, we'll cancel this delta T with this delta T. We'll have rho 1 A1 V1 into B1. For the time being, take B1 equals to 1. So rho 1 A1 V1 is what? It is the mass flow rate, right? So B1 is representing the amount of the property entering the control volume, and B dot out is representing the amount of property leaving the control volume.
Leaving the group.
So they are basically inflow and outflow of the property from the control volume. The change that is happening within the control volume is governed by these two. Is it clear? Is this formula and this formula clear? ये जो equations आ रही हैं आपके सामने clear है? Limit delta t approaches 0 and b dot out.
Yes, sir, clear.
Yes, sir, clear.
So what we have on the right side is now the d by dt of p system. We got this by applying. We're taking its derivative equals to partial by partial t of the B control volume, not like that, O B dV over the control volume plus rho, not rho, B in B dot in minus B dot out. The physical explanation of this is called the Reynolds transport theorem. This is helping us to relate the system quantity with the control volume, the system property with the control.
B dot in, excuse me, sir, B dot in negative नहीं होना चाहिए सर, हमारे पास B1 नेगेटिव था इक्वेशन.
Sorry, इसको reverse. B dot n. ये भी हम ये साइन अभी इसकी एक्सप्लेनेशन जो है थोड़ी सी, जब तक हम b को डिफाइन नहीं कर लेते ना तब तक ये एक्सप्लेनेशन साइन जो है बस इनको इसी तरह याद रख लेंगे. अभी माइनस और प्लस है, बट वी नीड टू हैव द राइट साइन ओरिएंटेशन फॉर दीस. उसके लिए हम एक वेक्टर डिफाइन करेंगे, दैट वी विल डिस्कस इन डिटेल के वो साइन कैसे आ रहा है. जब तक हम b प्रॉपर्टी डिफाइन नहीं करते b है क्या चीज, ठीक है. तो इसके लिए b सिर्फ आप दिस इज द बेसिकली रेनॉल्ड ट्रांसपोर्ट थ्योरम. अब ये बता क्या रहा है कि जो भी चेंज सिस्टम के अंदर आ रही है, व्हाट इज हैपनिंग इनसाइड द सिस्टम डिपेंड्स ऑन थ्री फैक्टर्स. Rate of change within the control volume with respect to time, the unsteady effect, partial by partial t term, this first term, and what is going out of the control volume and what is coming into the control volume, right? At which rate? The rate at which the property is going out of the control volume and the rate at which the property is coming into the control volume, the difference of that, the net mass flow rate. Okay.
Yes, sir.
So the first term is the unsteady term, and the other two terms are the mass flow rates. Not the mass flow rates, but the property flow rates. Whatever the property we will decide. This expression is valid for fixed control volume because we have defined that it is fixed control volume, and this is only valid for one inlet and one outlet. If there are more than one inlet and more than one outlet, what we'll do? We'll talk about the net. We'll combine the sum of all the inlets, and we will all combine the sum of all the outlets, and then we'll make them one inlet and one outlet. Clear?
सर नेट किस तरह, मतलब ओवरऑल सम करके
जितनी भी mass enter हो रही होगी, we will add that all, the amount of property all. Let me explain it here. Let's say if it was like this, I had an inlet here as well, I had an inlet here, I had an inlet here, and there was one outlet here, there was one outlet here, and there was, let's say there were two outlets and one inlet. So what I will do, I will add these three. I will use the net in m, if it is mass flow rate, m dot net in, and similarly I will add these two, and I will use net out if it is mass flow rate, depending upon the definition of the B. Clear?
Yes, sir, clear.
So if I write the general form of the Reynolds transport theorem, you are on your screen, you are seeing the general form of the Reynolds transport theorem. Now that is very interesting to understand. Let me explain this one first and then now we can combine the flow rate terms. So what we have done, we have combined the B dot out term minus B dot in term. How we have done this and what's the explanation beyond that is like this. I will explain it with 1B. We know that B dot out is rho area into velocity, right? Is it so?
Yes, sir.
If I say I don't know if it is an outlet or if it is an inlet, then B dot would be rho area into velocity, right? Because we are based on B dot out, we are adding a positive sign here, and based on B dot in, we are adding a negative sign here, right? For the time being, I say I don't know what is B, if it is an inlet or if it is an outlet. I am not clear about that. So what I do, I just take velocity vector and take its dot product with a normal vector, normal to the control surface. So if V dot n is positive, what it will mean?
सर अगर पॉजिटिव है तो आउटलेट होगा.
If this is the control surface and the mass is flowing like, let's say the property B is flowing like this into it, the area normal of this surface would be always outwards, right? Area normal हमेशा outward होता है. किसी भी surface का उसका area normal हमेशा outwards होता है. So in this case, V dot n would be anti-parallel, right? Would be negative. Is it clear? In this case,
Yes, sir.
V dot n would be negative. That is less than 0. Negative sign. फिर जब यही फ्लो रेट इसके क्रॉस चला गया तो अब क्या हुआ? अब एरिया नॉर्मल यहाँ पे इस सरफेस का देखेंगे आप, राइट? सरफेस की दूसरी साइड का. In that case, they are parallel, and V dot n would be
positive,
greater than 0. So it would be an outflow. Clear? There
सर
can
ये
be
थोड़ा रिपीट कर देंगे इसको. एरिया नॉर्मल है.
ये आपकी और समझाने के लिए हम इसको ऐसे कर लेते हैं. लेट्स से दिस इज अ चैनल, ठीक है, इसमें से फ्लो इन और आउट होगा. एरिया नॉर्मल इज ऑलवेज परपेंडिकुलर टू द सरफेस. अगर आपके पास आपका मोबाइल फोन है, इफ यू हैव योर मोबाइल फोन एंड यू प्लेस इट ऑन योर हैंड, द एरिया नॉर्मल वुड बी पॉइंटिंग टुवर्ड्स द रूफ. ठीक है, समझ आ रही है? The area normal of anything that is horizontal would be in your room would be pointing towards the roof or the ceiling of your room, and the area normal of your ceiling would be pointing towards the floor of your room. ठीक है?
Yes sir, सही है.
Area normal of the wall that is in front of you would be pointing towards you, right? So area normal is always perpendicular to the surface. So in this case, this is a two-dimensional body and there is flow across it. The area normal of this left surface will be pointing towards this direction, and the area normal of the right surface will be pointing in this direction, right?
Yes, sir.
So if we have flow from this side to this side, here the area normal, that is n vector, is anti-parallel to the velocity vector, right? So v dot n would be negative for inflow. And on the right side, v and n are parallel, so v dot n would be greater than 0. Clear?
Yes, sir. Clear.
Moreover, this v dot n will solve many other problems. Let's say if this control surface is like this, what is happening? The area normal would be like this, right? And if the flow is horizontal, like this, it means that whole of the surface is not participating in flow. So v dot n would be equal to v cos theta. So it will automatically account for the amount of flow, because the flow beyond this area would pass above, right? That will not contribute to the control volume. And if there is another case, like if the control surface is horizontal like this, the area normal would be vertical like this. And if the flow is like this, horizontal, then v dot n would be, what would be v dot n here?
0, 0.
So 0.
Equal to 0, because there is no inflow or outflow. Clear? So that's why we have simplified it from rho AV to v dot n by using this area normal vector. Clear?
Yes, sir.
So we can write it in a single term. So this is the description of the most generalized form of the Reynolds transport theorem. Is the Reynolds transport theorem clear? Any question in that? The inflow and the outflow part and the unsteady part, the derivation. Any question in that?
Clear
सर ये जो हम फाइनल सर जो कंट्रोल सिस्टम की सर हमने एक ही टर्म बना ली है इंटीग्रल में, इसमें हमने आउटलेट फ्लो दोनों को कंबाइन कर दिया है, नेट फ्लो ले लिया है.
Yes, net inflow or outflow. Net change कह लें, not net inflow or outflow. We are basically talking about the net change in the system. It can be positive or negative, and now it is generalized. It does not limit that. Okay, there is only one inflow and one outflow. There can be infinite many inflows and there can be infinite outflows. We will be encountering in this term. We will only be having the net, the overall result. That can be positive or negative. That will automatically be included here. Clear?
Yes, sir. Okay.
Any question else?
सर ये जो आउटलेट या इनलेट का जो साइन है, ये सर ये इसी से ही कम करेंगे ना, v डॉट n से.
Now v dot n will decide. Yes, if there is only v dot n is negative, it will mean it is
inlet.
And if v dot n is positive, it means it is
outlet.
एक्सक्यूज मी सर, ये थ्योरम ये किसके लिए एप्लीकेबल है? यानी ये इसके लिए बाउंड्रीज जो है नॉन डिफॉर्मेबल होनी चाहिए या फिक्स्ड होनी चाहिए या
fixed non deformable? Right now it is only valid for fixed non deformable. We will discuss its modification for the moving control volume as well. There might not be any modification, but there will be some like mathematical simplifications to that. So we have just discussed this, if the control surface and the relationship between the normal vector and the control surface. What is happening? We will further discuss that. What is, if the flow is steady, then there will be no change. Basically, now what's this term is representing? This first term, partial b by partial t, partial by partial t of the control volume. What is happening inside the control volume? We should say that only control volume, there should be no change in the control volume. That is, there is the control volume is fixed. The volume, the control volume is always equal to the system because there is only inflow and outflow. There is no source or sink within the control volume. Do you understand this? That there, if the flow is steady, if the system is steady, it means that there is no change in control volume with respect to time. This term would be 0, the first term. There will only change in system because of the inflow and outflow, right? Is it clear?
Yes, sir.
For example, in order to explain, we take this B as temperature of the system. So the temperature of the system will only change when there is
Change in temperature.
when there is some hot fluid coming and there is some cold fluid going out, right? These can be two possibilities, that if there is some hot fluid coming into the system or if the cold fluid is going out. These two are the possibilities for changing the temperature of the system. But what happens if I place inside the control volume a sink? A sink, like let's say there is no inflow into the system, but there is no outflow to the system, but still the temperature is changing. Then it means that there is some sink in the control volume. There is some thing that is absorbing temperature within the control volume. Let's say if I have placed a piece of ice inside the control volume, that would be reducing the temperature, right? So that will include the unsteady effects. This term, the first term, is expressing the unsteady effects, the source and the sink within the control volume. Or if I place a heater inside the control volume, the temperature will rise with time. Also, if there is no inflow or outflow of the hot fluid. Clear?
Yes, sir. Clear.
Yes, yes.
So in the next class, we'll be replacing this B with different properties. Let's say we'll replace it with the mass. We'll replace it with the capital B with the momentum. So we'll have the three famous equations of Reynolds transport, three famous equations of the fluid mechanics: the energy equation, the continuity equation, and the momentum equation. We will see how when we replace B with M, which equation we get. We will get the continuity equation. When we replace B with velocity, we'll get the momentum equation. And similarly, when we replace B with another property, we'll get the energy equation. So there can be different equations. We'll study how these equations are important in fluid mechanics by further discussing the Reynolds transport theorem and its application. Clear? We'll also solve some problems related to the Reynolds transport theorem as well.